This video is a deep dive into the long division techniques for algebraic fractions. If you have stumbled upon this, expect a variety of methods which can hopefully equip you to better navigate through the darkness of your schooling years. We have to start with the easiest method here, plain old long division. Let's contrast this with 1000 divided by 70 for simplicity. Notice the zeros here, representing 0 hundreds and 0 tenths. This concept of place value applies if we were to divide x cubed plus 4 by x plus 3. Keeping the descending degrees in mind, we allocate slots for 0x squared and 0x even though they aren't there explicitly. Now we begin. Observe how I start with a quotient of 1 in the tens place, as 70 times 1 gives 70, a value closest but not exceeding 100. This is so that I can obtain a difference between 100 and 70. Compare that with the algebraic expression here. I start with a largest quotient of x squared, as x plus 3 times x squared gives x cubed plus 3x squared, a value closest to x cubed plus 0x squared. When I do a subtraction, observe how the x cubed terms are eliminated, leaving a difference of negative 3x squared. Back to the numerical example, notice how the digit 4 is carried over to form 304. This means I need a quotient of 4 to obtain 280. When subtracted from 304, it leaves a remainder of 24. Using the same technique, we carry over the next term 0x to form negative 3x squared plus 0x. A quotient of negative 3x works here, as x plus 3 times negative 3x gives negative 3x squared minus 9x. Once again, when finding the difference, negative 3x squared is eliminated, leaving positive 9x. But we are not done yet. We still have the final term plus 4 to carry over to form 9x plus 4. That will require a quotient of plus 9, as the product yields 9x plus 27, a value closest to 9x plus 4. The difference upon subtraction of negative 23 is finally the remainder. So, what are the strengths and weaknesses of this skill? If you only have time for one technique, use this. It aligns closely to basic arithmetic and hence is easiest to understand. The drawback, as you can see, is that the working could take up a lot of time and space. But now, as we pause for a moment to think about it, how can we trust the process that it was sound? We know that the improper fraction 1004 over 70 can be rewritten as 14 and 24 over 70, with the dividend, quotient, remainder, and divisor as shown. Click the link above for the previous video if you need to review the format of long division. From a numerical standpoint, the remainder has to be less than the divisor. Since we know that 24 is lesser than 70, the long division is sound. What about the algebraic fraction then? Once again, we can map the dividend, quotient, remainder, and divisor as shown. But our problem now is that we have no basis to compare the remainder and divisor. How could we establish that negative 23 is lesser than x plus 3 when x is a variable? Thankfully, recall from the previous video that we can compare the degree instead. X plus 3 naturally has a degree of 1, and since negative 23 is a constant, it means it has a default degree of x power 0. And now, since the degree of 0 is lesser than the degree of 1, the long division calculations are valid. We should move on. Holding on to the fact that the remainder's degree has to be lesser than that of the divisor, we move on to the second technique. From the format, we know that the four terms have to be positioned in this manner, with two spaces allocated for the quotient and remainder. Now, based on the dividend's degree of 3 and divisor's degree of 1, how large does the quotient have to be? Reverse multiplication would suggest that an x squared term is needed, so it has to take on the format of ax squared plus bx plus c. What about the remainder? Recall that the divisor has a degree of 1, and for a logical long division, the remainder's degree has to be lesser than 1, which is 0. So I only have to carve out a slot for a constant, which I can name as d. It's evident that this is a very short and abstract method. Simply eyeballing the degrees to infer the size of the unknowns is concise, but there's still the problem of solving for these unknowns. Speaking of eyeballing, here's what needs to be done to solve for a, b, c, and d. Starting with the x cubed coefficients, we can see a value of 1 on the left hand side. Who else corresponds to x cubed on the right hand side? The only culprits are ax squared times 1x. The only worthy conclusion here is a equals 1. What about x squared coefficients? Look closely at the left hand side. What x squared terms do you see? Exactly, there are none. Which means that x squared terms on the right equates to 0. We have ax squared times 3 over here, and also bx times 1x as our x squared terms. That means 3a plus b has a value of 0. Thankfully, we have solved for a earlier, so b takes on the value of negative 3. If you have gotten the hang of it, you'll see that we are solving for coefficients of x next. There are none in this example, so that means bx times 3 added to c times 1x equate to the value of 0. Our prior value of b equals negative 3 will help us solve for c. Moving on, only constants left. The left hand side has a constant value of 4. It has to balance out with those on the right, namely c times 3 added to the d term on its own. Since 4 equals to 3c plus d, and we know the c value from before, we can solve for d equals negative 23. And as you can see, the second method leads to the same outcome. So far, both methods shown are rather time-consuming. Synthetic division, on the other hand, is a faster method if you can master it. Using the same example, we structure the working like this. Keeping the place values in mind, we only need the corresponding coefficients for the dividend, which in this case are 1x cubed, 0x squared, 0x, and 4. As for the divisor, we need its value when equated to 0, in this case, the value of negative 3. To start the working, copy the first coefficient you see here. Then, find the product of negative 3 and 1 and write it here. Sum up both values in this column. 0 plus negative 3 is negative 3. Repeat now the multiplication for negative 3 and negative 3, which yields positive 9. Write it in the next column and find the sum. And again, the product of negative 3 and 9 in the next column. The sum of 4 and negative 27 is negative 23. If these numbers look familiar, that's because negative 23 is the remainder, while the numbers 1, negative 3, and 9 are the coefficients of the quotient in descending order. This method is definitely more space-saving as we only deal with coefficients with no algebra involved. On the flip side, it is more abstract to grasp and only works for linear divisors. And now, the final method. Remainder theorem only works if you have an idea of functions. Using the same example once again, we start by representing the dividend as a function of x. Remember the divisor in the previous method? Assign it a value of 0 for the numerical value of negative 3. The concept of functions allows for the value of negative 3 to be substituted into the expression. Negative 3 to the power of 3 plus 4 gives negative 23. Hopefully, you can now see why this is called the remainder theorem, as the value of negative 23 should be highly familiar by now. But why did that method work and what exactly does it mean? To find out, we need to know what the curve of x cubed plus 4 looks like. Here it is if superimposed on a Cartesian graph. A cubic curve with an inflection point at the y-axis curving upwards. The value of x equals negative 3 would be in between negative 2 and negative 4 on the x-axis. If I were to extend a line to the curve, look at the corresponding y value. The divisor and remainder are actually the coordinates of the graph. This graphical method is a helpful way to illustrate how the dividend, divisor, and remainder fit together. The only drawback is that the quotient cannot be found. And at this point of time, I think we should be ending this journey soon. In conclusion, the right tool for the right job. Remainder theorem is by far the simplest method, but synthetic division offers the chance to review everything. Just don't confuse the operation signs here with long division. Observing the format is another direct method, but you have to be good at algebra for this. If all else fails, long division will be the most trustworthy tool to master. Click on the video card on the right if you need an introduction to long division. And with enough practice, you'll never have to revisit this deep dive ever again.